Thank you very much for the introduction, Alicia, and thank you again for inviting me for this Congress. I'm very honored to be here. So yeah, you can see here the beautiful picture of Colorado Mountains. So I will talk a bit about renewable energy systems, but the main focus will be on the optimization methods related to the problems associated with these systems. So let me give you a bit the background on the emerging modern energy systems, very high level background. So these systems are characterized by widespread adoption of power electronics based devices, which appears on the edge of the system, on the edge of the power network, if you want. Things like wind farms, solar panels, storage devices, appliances, smart appliances in your houses, right, and electrical vehicles. And these systems are becoming more and more characterized by intensive use of communication, control, data, and information, and becoming highly distributed by the nature of these distributed energy resources that are spread in this system. And overall, they are more complex to operate safely, securely, and optimally. But of course, on the other hand, there's a lot of opportunities associated with the systems because we can control more things in addition to the fact that they become more complex. But let me focus a bit on the complexities here. So the complexities associated with these systems, first of all, are complexities related to ambient and operational conditions. You can think about solar panels that are not completely deterministic, very volatile, and can be affected by weather. And of course, equipment that is out there in the field, in the system, such things like electrical vehicle charging stations that can go out of operation. The second complexity category is actually the size, right? So if you think about the power network itself, the power network didn't change for hundreds of years. But what changed is actually the number of control points in this system, right? So if before that we had maybe thousands of big power plants that we had to control, now we have to control suddenly millions of all these devices that are out there. So size in terms of actually the number of control points or optimization variables, if we're talking about optimization. The other types of complexities related to interactions between different systems or subsystems, right? So you can think of physical systems such as wind farms, which affect each other because they appear in the way of the wind, and the wind comes in different ways to different wind turbines in this wind plant. But we also have interactions with logical systems and with societal systems associated with energy systems. And in the context of all these complexities, the main research questions that we at NREL in my group are trying to answer is how you can control and optimize all these massively deployed edge devices or distributed energy resources in real time. And if you want to read some high-level thoughts and description of this research, you can read this recent article in IEEE Power and Energy magazine last year. But what I will focus in this talk is really on mathematical foundations related to optimization of such systems. And I will start with really an abstract description of the problem, but I will connect to energy systems. I will also be happy to hear thoughts about connections to other systems, because the methods that I will present here are actually general and they apply to any system, complex system, network system. So let me start with some mathematical notation that I will use throughout. So consider now a system, general system that can be described by just an input-output relationship like this, where Y is a vector of system outputs, X is the vector of controllable inputs, and the mapping H maps inputs to outputs. In this case, I assume it's a time-varying algebraic map. This can be also extended in general to dynamical systems, but I will focus here only on simple algebraic relationship between input and output. To connect to power systems specifically, just for, this is very high level, even for people that don't know anything about power system, but I can give a bit high level background here, what power system is. what I show here on the left is actually the network, a distribution network, what we call in power systems world. And this is a power network that delivers power to the customers in the neighborhood, for example, right? So here at the head, here at the top, you have a substation that transforms power from high voltage to low voltage. And then the power is delivered to the customers, and each node in this network represents, for example, a house in your neighborhood. Okay, so this is a graph that represents a neighborhood and a distribution network associated with it. And in this network, you can think that you can have houses with solar panels, electrical vehicles, smart appliances that can consume but both generate power, right? So this is the world of new energy systems where the energy can be generated on the edge of the system compared to previous classical power systems world where these systems were completely passive, they were just consuming power. And in this context, if we want to connect to the mathematical formulation of input-output relationship, we can denote by X the power that is injected by controllable devices in this network. So basically, plus or positive number will represent a positive power that is injected into the system, for example, from a solar panel into the network. A negative number will represent consumption of power, the classical case where you have just devices that consume power in your house. So this vector X will represent all these power injections that you can control in the system. Y, the output, a typical definition of an output in such a system would be voltages, voltage magnitudes if you want, or just voltages inside this system. And the voltages represent typically how good the system operates, right? And how healthy the system is, right? So voltages should typically be within some bounds. And the mapping H that connects input and output is, for example, a mapping that physically describes the physical laws of the system. In the power systems world, this is called power flow equations. And these equations are derived from basic laws, physical laws, right? The things that connect currents, powers, and voltages, such as Ohm and Kirchhoff laws in this system, right? But we can abstract it with the mapping HT. And in these systems, the driving signals are things that we cannot control. For example, the load that we have in the power system. And for example, if you have solar panels, then the available power from these solar panels. Basically, what I show here is a typical graph of how sun, during the peak hours, you have power that goes up with the sun and goes down at night, right? So that's these are the classical signals. And we can see that these things are time varying. So this is why also everything that's related to the system is time varying. That's why I'm adding the index T here, which represents time varying relationship between inputs and outputs in the system. So let's go to the optimization question. So the desired behavior of such a system, we can abstract the problem. This is, of course, a simplification. We can complicate it as much as we can, but the main ingredients are shown here, right? So what we are trying to do when we do optimization of such systems, we trying to minimize some cost. Let's call the cost F T. F is also a time varying cost. And I represent the cost only in terms of the output Y, but of course, again, we can complicate it and make the cost also dependent on the input. And in terms of constraints, we have constraints on the input. Here I represent them implicitly using this set calligraphic XT and the physics. So Y equals H T of X represents the connection between input and output. So this would be a typical problem, optimization problem that you can write to define how you optimize the behavior of such a system. And connecting to power systems world or energy systems world, just again to give a flavor of what kind of problems we are dealing with in power systems. Again, take these power systems on the left and define the following optimization problem. For example, optimize the generation cost and customer satisfaction subject to device constraints. So this calligraphic X here would represent device constraints. For example, you cannot draw more than some amount of power from a solar panel or less than zero power from a solar panel. And this will represent the device constraints. Basically, these are hard constraints that have to be satisfied at any given moment. But also there are physics that connect voltages to powers, for example, through power flow equations, right? So these are the constraints that we have in this optimization problem. This in power systems world is called optimal power flow. It's just a name, but this is a very famous name in power systems. So let's dig a bit into just straightforward approach to solve these kind of problems. Right, we have this problem. Again, I just want to emphasize this is a time-varying problem because of time-varying conditions that I showed, for example. And what, on a high level, what we need to do in order to solve such a problem? Suppose that we want to optimize all the power generation from all these millions of devices in the system and to minimize the cost, right, subject to physics. So what we need to do, we actually need to do main two things, right? First of all, we need to know the function h. In some sense, we need to know how voltages are connected to powers. In other words, we need to know the topology of this network. We need to know the parameters of all the lines in this system. And then we can construct this function h based on physics law. We can do it, but this requires a lot of information. And as a byproduct, in addition, we also would like to know probably the Jacobian of this mapping h, which represents the sensitivities of output with respect to input. Basically, because we will typically need to compute gradients here, right? And once we have this information, we can, at any given time instant t, run a projected gradient method, for example, right? It's just an example. You can use any other method that you want, but you can run a projected gradient method to solve one, where at each iteration k, here k represents iteration, I just project the gradient update. Notice that explicitly in this gradient update appears the Jacobian of the physics, J of ht, because of the chain rule. I wanted to write it explicitly, specifically for the purpose of the next steps. And then the gradient of the objective function evaluated at the previous iteration, right? So that's nothing new here. It's just plain the gradient descent applied to problem one. And of course, if you have all the information and you have all the time in the world to solve this problem, you can do it. But this is actually what is in power systems world before was called an optimal power flow, right? But in this new world of these emergent energy systems, actually we are coming to the situation where we are not able to solve this problem to convergence and especially in real time. So this is what I want to focus on in the next part of this presentation, is to show ways how we can make these algorithms be able to run in real time and with as less as much possible information about the system, right? So these are the two main constraints that we have, right? So first of all, how do we do it in real time? Do we have enough time to run this iteration to convergence? For large problems, we probably won't have enough time because we would like to solve this problem, for example, on a second-by-second basis. This is a typical time scale for variability, for example, of solar and load in these kind of systems. And the second challenge, as I mentioned, is do we have all the information? Do we have the model? What I will call model typically will mean just this mapping ht. Do we really have the model information in real time at any given time ht? And model here means that you need to know, again, as I mentioned, the topology of this network system, all the uncontrollable inputs at all the nodes. For example, your consumption of the house at any given moment, or when you charge or discharge your electrical vehicle and stuff like that. And topology, right? In other words, this system here that I showed here, right? The mapping ht represents, in addition to many things, also the topology, the connectivity between the nodes and the parameters of these lines. And in typical classical situation, practical situation, you don't have all this information in real time because of changes in topology because you don't know exactly what are the parameters of the lines and so on and so forth. So the approach that is becoming more and more popular, and we at our group here at NREL, we started in parallel with some other groups also in the world to look at this approach, which could be defined as model-based feedback optimization. Okay, so this is in some sense a marriage of optimization and feedback control in a very particular way that I show here. And I will just continue for a moment to illustrate these ideas on a simple gradient descent algorithm. I will go later to a more complicated problem, but for now allow me to just still keep this very simple. And remember our previous gradient descent algorithm. So the idea here is very simple conceptually. Instead of solving the optimization problem in an open loop fashion, I am putting the optimization algorithm in the feedback to the system, and I am allowed now to measure the output of the system in real time. So this is what I pay for this. But what I gain is that I can replace here in the optimization algorithm the mapping HT with the measurement of the output. Okay, so I just remind you that originally in this gradient descent algorithm, I need to know the mapping HT to run it, right? Now I just use the system itself in the feedback to the optimization algorithm, or if you want, I use optimization algorithm and the feedback to the system, depends on how you look at it. And I'm using this measurement and I'm plugging it inside the gradient descent, and I'm doing one iteration per time step. So here, this is an online optimization approach where at every given moment, I'm doing one step of optimization. I'm measuring the output. I'm plugging the output inside the gradient of the cost. And I go further next. And this is kind of an online optimization with real-time feedback to the system. And as you can see, this allows me to avoid, I don't need to know the mapping HT, let's say, right? Here, I pay the price, of course, that I need to measure now the output, but I don't need to know how X is related to Y directly or explicitly, which means that for example, I don't need to know in principle the topology. I don't need to know the uncontrollable inputs such as power consumption at the different houses. I just need to measure the output. And I remind you that in our case, the outputs, for example, the voltages at selected locations in this network. So I can measure the voltage, I can act on the voltage, I can produce a new controllable input, then again, I measure the voltage and so on and so forth. However, I still call this approach model-based. And I hope you can figure out why. Right? Although I replace the model here, but notice that I still have this J here, which is still required, right? Because of the chain rule. I still need to know what is the sensitivity of the output with respect to controllable input. This is a bit of a less of a requirement, right? Because this is just means that I need to know the sensitivity with respect to controllable inputs. I don't really need to know the uncontrollable inputs. I don't need to know other things, but still it requires some significant information about the system in terms of this Jacobian. So this is still in between this approach, right? It's kind of in between completely open loop model-based approach and completely model-free feedback approach. So this is just to pay attention here. So to move to completely model-free world, what we can do is really move from gradient-based algorithms to zero-order algorithms, right? So this is what I will show next. And the idea is, again, conceptually simple. Okay, I have this function, right? Remember, this is a composite function. I have a cost F of the output of the system. H represents the output mapping. Eventually, it's a composite function of X. And I, in principle, would like to take gradients of this function, which unfortunately result in this form where I have H and J of H. Instead of doing that, what I suggest is, okay, let's take a zero-order approximation. And zero-order approximation essentially is a fancy way to do numerical differentiation, right? So, and here I give a couple of ways to do it. And again, this is not an exhaustive list, but I will use one of them to illustrate the algorithms next. So let's first start with very simple, the most simple way to do a zero-order approximation of the gradient, which is based on a single evaluation of the function. And this is written here. So you can see here two new parameters that I have to add to this construct, epsilon and xi. So xi is, we can call it an exploration vector. So what it does, it tries to explore the function around a given operating point. So this is, we can call it exploration or perturbation vector. And epsilon is just a scalar parameter that controls the magnitude of this perturbation. But eventually this single evaluation approximation to the gradient is, as you can see, is based on evaluating the function at a perturbed location multiplying by this perturbation vector. 1 over epsilon just scales it. So it's just to make things comparable to the actual gradient value. So this is single function evaluation approximation. The next thing that I would like to show is the two function evaluation, which is probably the most intuitive one, and I will use it in a second, which is very similar to numerical differentiation, right? I take the value of the function at plus delta, I take the value of the function at minus delta, I subtract and divide by distance. The only different thing here is that this vector xi appears as a multiplication and not in the denominator. But it is very similar idea. And I will focus on this two function evaluation approximation for the reason that I show here, again, very briefly. The motivation for this, specifically for two function evaluation, is that we can show that this definition here of the approximation of the gradient is actually a low rank matrix. So xi times xi transpose is a rank 1 matrix, right? I do the outer product of the vector xi times the gradient. So this matrix is positive semi-definite, but it's low rank, unfortunately. But still, it means that we are in the right direction of the gradient, right? We multiply the gradient with positive semi-definite matrix. And there is an error term of the order of epsilon squared, which is inevitable in general for general functions. However, this term is 0 if you have a quadratic function. So this is a motivation for using this kind of approximation of the gradient. You can use more evaluations. I didn't mention that, but you can use more function evaluations, more than 2. This will reduce the variance of the approximation. However, this of course comes on the expense of more evaluations, right? So 2 evaluations is kind of a good trade-off here. So at every time that you need to compute the gradient, you do here only 2 evaluations. And you get a nice approximation, let's say. So yeah, so that's kind of just the roadmap of what I will show also in more detail and with more complicated problem, constrained optimization. Before I go there, I just want to just put things in context, right? This is not something completely novel. You know, people looking at how to do model-free optimization in general for almost, I would say already a century, right? 1922 is almost a century. So this is when people started looking, I think the origin of the so-called extremum seeking can be found in this paper if you read very carefully. I was not able to find it there, but some people say you can find it. But if you really want rigorous origins, I think 1952 is one good paper from Kiefer and Wolfowitz, who proposed very first this kind of algorithm, which uses, I think, 2 function evaluation. But there is a long history, and recently there is also a lot of interest in machine learning community for zero-order methods because of all the complicated machine learning problems, which are non-convex, very hard to optimize, and zero-order methods very frequently are very useful because you just need to evaluate the function and you don't need to really compute gradients or know the actual structure of the function. So specific focus for our work is really constraint and time-varying system optimization. As you can imagine, in energy systems, you cannot do unconstrained optimizations. Everything is constrained. You cannot ask the device to produce infinite amount of power, right? So everything is constrained. And time-varying because of the volatility of all these new energy systems with solar and wind and high variability of load because of, for example, electrical vehicles. The other point that I want to make is that you remember this perturbation signal C. There are many ways to define it. The more classical way is to do random exploration. You just choose a stochastic process for this C, or just draw it from Gaussian or unit sphere. There are different ways to do it. However, in our work, we specifically focus on deterministic exploration signals for reasons that I think I will mention later, but I can give you just a flavor of this. It turns out that with deterministic exploration signals, specifically with sinusoidal signals, you can obtain faster convergence rates. And this is very important for real-time optimization, because if you just want to, in few steps of gradient descent, you want to arrive as close as possible to the optimum, you want fast convergence, right? So the other part is that, yeah, we are talking about, as you saw in the beginning, about online optimization, right? Because we are acting with the system and the feedback, and we will be defining primal dual methods to deal with constraints. And here, this is just a list of papers that cover some of these topics in the recent years. They all appear in the slides. So let me now go to a more elaborate problem that we really solve. Of course, I showed you a very simplified problem, but this is a kind of a problem that we solve when we talk about optimization of networked systems in general, or specifically in our research domain related to power systems. And a network, so here I'm describing an optimization problem that associated with n systems that are interconnected by a network. And whereas before the desired behavior is defined by this time-varying optimization problem, I think here, yeah, I used index k to superscript k to define a time index, a discrete time index. And you can see here that the input x, the vector x, is now comprised of n subvectors xi, each representing an input to a subsystem xi. Each subsystem has its own constraints as before. There are coupling constraints through the output y. So y of x is actually the mapping h that we saw before. And there is some constraint function g that couples all the inputs through this relationship. And in the cost, again, as before, there is a cost of the output, but there's also a cost of individual inputs, as I mentioned, so we can complicate this problem to this extent. And this is, as much as I can complicate it, because typically this is a structure that you will have. You will have an individual costs of individual devices, and you will have some coupling term associated with the output. And this sum is reasonable here. So the separability here is reasonable. Okay, so now we have this more complicated problem. Obviously, we have some constraints here, such as for C, that we would like to dualize because of obvious reasons, right? Unless we are able to project on these constraints, we will not be able to solve this problem. So what we are doing here is really going to the primal dual formulation, and we are defining a desired trajectory of this optimization problem, right? Notice again, I call it that trajectory because I have a time index k. Obviously, for each given k is just a desired solution of this optimization problem. But this is a solution of the max mean associated with this optimization optimization problem. And L here is a Lagrangian associated with this optimization problem. So here in this specific formulation, I dualized this constraint for C. And this is the, I didn't write a Lagrangian, but I guess people understand here what Lagrangian means. The only thing that I want to point out here that we are not using the straightforward definition of the Lagrangian, but we are using the regularized Lagrangian, which of course shifts the solution from the optimum, but it has these very great properties that we can enforce a regularity here, right? So what we are doing that in case I had to tell originally, of course, that all the elements here are convex. We assume that the functions are convex, the constraint functions are convex, and the sets are convex. And if they are not convex in the original problem, we have to convexify. But in the problem 4, I assume that it's a convex optimization problem. But it is not necessarily strongly convex. So if it's not strongly convex, I can add this regularization term for the primal variable x norm squared. And I also am adding a strongly concave term in terms of the dual variable to make the Lagrangian strongly convex, strongly concave. And this is for the purpose of designing the algorithms, right? Of course, this shifts the optimum, but we can, of course, control this shifting by controlling the P and D. So if we set them small enough, we will not be too far away from the optimum. But of course, this comes, if I add these terms, I will have much faster convergence because of the strong convexity or strong concavity in the dual variable. So using this formulation, I can now define a first order, first of all, primal dual algorithm to solve these kind of problems. Again, this is a first order algorithm that is based on measurements of the system output. Okay, again, this is a feedback-based approach. So what this algorithm does is, as is described in these steps. So first of all, at each time step k, we apply a given input to the system, xk. Then we collect the measurements of the outputs. Remember this y hat. Then we compute the gradient of the Lagrangian. Again, notice that this gradient of the Lagrangian depends on the measurements of the output. So this is a feedback-based approach. Then we compute the primal step, going in the direction of the negative 2, the Lagrangian gradient. And we compute the dual step, where we go in the direction of ascent in the dual variables. So this is just a simple primal dual algorithm applied to the Lagrangian, to the regularized Lagrangian. Notice the regularization terms here and here, but with feedback, right? Again, I just want to emphasize. So these blue parts represent where I insert the information from the system output, y hat. It's before, as before, right? Before that, we had just the gradient descent. Here we have primal dual algorithm, but things didn't change much. We just insert the feedback where we need it inside these two updates, in the primal update and in the dual update. There is a hat here, supposed to be here as well. The hat here appears because we assume that we measure the output, but the measurement, of course, is not necessarily exact, right? So there might be a noise. So if the measurement is exact, then you will have an exact gradient here. Otherwise, this is an inexact gradient. So let me just take this algorithm and convert it to the zero order method using the two function evaluation approach that I mentioned. And the only place where we need to do it is actually here, right? In this gradient, J, right? Here, we still have the problem with J. We need to know the Jacobian of input to output. And we do the following. Again, it comes on expense of more measurements, right? So in the first step, we need to apply two inputs to the system, one with plus delta and one with minus delta. And then we can collect the corresponding measurements. I assume that we can do it fast enough, and I don't change the index time index, right? So I just say, okay, this is, I can probe the system in the same instance. Of course, it's an approximation, but for the purpose of to make it less complex, I assume that you can do it at the same time. And then we approximate the gradient with a zero order method. It's just what is written here, right? We have this signal CK. Remember, this is the exploration signal, two-function evaluation for the primal part. So this is the objective function, remember, the F0. But we also have the zero order approximation for the dual part, for the constraints. But this is the same. And primal dual steps remain the same. Nothing changed here. The only thing that I changed is how I compute this gradient. And this algorithm is completely model-free, right? So I have a system, I probe it 2 times, I do 1 iteration of primal dual algorithm, I go to the next time step, I do again the same thing, and I don't need to know anything about the system, well, anything about the physics of the system, right? Of course, explicitly I kept the graphic X because these are the constraints that I assume that I know, such as, for example, if you want to optimize your solar panel, you know that you cannot go above some rated power of the solar panel, or if you have an appliance, it has some rated power that you cannot exceed, right? So these things we know. And I don't go into the details, but these algorithms, primal dual algorithms like that, we can also make them distributed, right? So this is kind of the main point here, is that we can have a distributed implementation of such an algorithm where only devices need to know their own information, such as this set X, and project on their own constraints, and there is no need of sharing all this information between different devices, or there is no need of a single entity that needs to know everything. The only thing that it will require still, right, this is not completely decentralized algorithm because there is coupling. Someone needs to gather these measurements and perform typically some computations that are associated with these measurements. But this central entity will not need to know anything about private information about the devices or homes or whatever you have in this system. So I think I have some time to go over this. So I just wanted to really touch real quick about convergence analysis of these kind of algorithms. So this analysis is based on what you can find in the literature as quasi-stochastic approximation. Again, I'm not going into the details, but the idea here specifically for how we did it was using deterministic, as I mentioned, exploration signal CK, which is, for example, a sinusoidal signal. And one assumption for analysis, which we can also in principle relax in general, is that if I take this signal, basically I'm sampling the CK from some continuous time signal, let's say CT, and if I take and I compute a covariance of this signal, a deterministic covariance in this case, right? I just have a sequence and I compute this outer product, I compute this covariance, there is some time period over which I will get an identity matrix. And actually, this is a very strong assumption, although we can still, for example, satisfy it with this kind of sinusoidal signals, you can prove it. But in practice, you can relax it, and instead of identity, what I really need is just a positive definite matrix. So we need to sum up these terms to a positive definite matrix. Remember, of course, all these terms individually, they are positive semi-definite, but over a given period of time, I would like to average them to a positive definite matrix. And this could be done through, for example, this sinusoidal choice. This is one structural assumption on this exploration signal. For analysis, at this point, we need to also assume that we do projection in the primal step only every t time units. T is the same as here. Again, this is because only every t time units, the approximate gradient really becomes gradient, right? Because you can see that after t time steps, the approximate gradient that we had there has an identity matrix as a multiplication, right? So remind you here, maybe just to make it refresh the memory here, the approximate gradient that we use looks like this, right? And we can prove that this is this. But at any given moment, this is a lower rank matrix times the gradient. But if you average this over a t time steps, this becomes an identity times the gradient, and this is where we have actually a real gradient step. So that is why, roughly speaking, right? I mean, I'm hand waving here, but this is why, roughly speaking, we have to assume this projection to be happening only every t time units. Although in practice, when we implement it, we typically project every time step, and it still works, but we cannot prove at this point the convergence. The third assumption here is the variability of the optimal trajectory. So this is just tells us how fast the optimum of this optimization problem moves, or if you want, it's a time derivative of the optimal trajectory, and I use this sigma to say how fast it is, and the gradients of the objective functions. Remember, objective functions also are time varying, so if they are not time varying, obviously this will be zero, but if you have change in the cost, you will have some variable EF that represents this change. And finally, for this analysis that I will present in a second, we assume that the measurement error, remember we measure output, we assume that there is some error, but this error is bounded by some quantity EY. There is also an option to do a stochastic analysis for noise, which I will not cover here, but here we assume deterministic noise. So the results, this is just a flavor of the results that you can obtain for these algorithms. Again, under some assumptions, I listed most of the assumptions on the previous slide, but the flavor of theorem is the following. You can say, you can find a step size. Alpha is the step size for primal dual, right? So this is just a constant step size here, right? So you can find the step size such that your trajectory, so Zk is the trajectory, the primal dual pair at every given time, is not far away from the optimal primal dual pair, which is Z star K, and the bound asymptotically is given by this quantity where this epsilon here is of the order of these different things that we defined. First of all, the order of time step, since we're using constant time step, it will appear there. Of the order of this epsilon squared. Epsilon, I remind you, was the magnitude of the exploration signal. So we need to control that exploration signal as well. EF is the variability of the gradient, and EY is the error in the measurement. And C eventually will be less than 1. So basically you can choose alpha so that this C is less than 1. So then this is standard geometric series eventually when you analyze this. And the convergence is, so this is asymptotic bound. So this is a neighborhood in which the trajectory will oscillate, but the convergence is exponentially fast because of the convergence rate is exponentially fast, or Q linearly if you want, Q linear, because of these regularization terms. So yeah, so that's just a flavor of the results. Let me go over the application. Again, I will, since I'm not sure how much people here know power systems, I will try to give you the essence of this application. I think I tried to give it in the beginning, but the idea is very similar. So what you see here on the left, you have this distribution system. Think about it as a neighborhood in a city, 123 nodes in this system. In this particular system, we had 8 solar systems distributed here, as shown in the figure, and 3 battery systems. And you can see also switches here. So notice this is a topology, but the topology can change at any time during the day because of some reconfiguration requirements, which are not out of control, right? You don't know in advance that they can happen. So what we're trying to do here is to show how our algorithm can adapt to these changes in the reconfiguration of the system, as well as to unknown elements here, because of course, in addition to 8 solar panels and 3 batteries, there are also 123 uncontrollable elements here. And I will probably skip the definitions. These just define mathematically what we would like to do. The main goal here is really, let me tell it in words, is to take this system and create a virtual power plant. So what is a virtual power plant? It's taking a distribution system, a neighborhood, and making it dispatchable in some way, or in other words, allowing it to follow given power profiles collectively, right, as an entity, as an aggregate entity. So this is what we are trying to do with this application here. But while we do this, we also want to respect all the electrical limits. So for example, again, here in the system, you have voltages. These are the outputs also in the previous formulation. And we would like to make sure that the voltages are within prescribed bounds. So here you have constraints on the output, as I mentioned in the abstract formulation. So this is all described here. What I want to show is really just some plots here that show how it works. So here on the left, you see the uncontrolled power that is consumed by the system at any given time during the day. And this tells us the total power. Basically, the power at the connection of this neighborhood to the higher level grid, the aggregate power. And you can see here two networks, network 1 and network 2. Actually, we had two, as I said, two different configurations of the network during this period, which means that it changes the system during this, the system changes during these instances. And the voltages of this uncontrolled system are shown here. So these are the voltages, normalized voltages. 1 means nominal voltage. Anything below 0.95 means bad. So voltage goes below limit. And you can see here that during the reconfiguration to network 1, the voltages actually went below 95, which means that there was voltage violation, which is not a healthy network. And similarly, during the period of network 2, there was voltage violation here because of high demand. Basically, when demand is high, the voltage goes down. This is, roughly speaking, rationale here. So if there is no control, this is what you will see in the system. You will see voltage violations during 2 periods of time. And what we did here with this real-time model 3 optimization, we did 2 things, as I mentioned, right? First of all, virtual power plant. So what is virtual power plant? I'm just saying, okay, I don't want to see this total power anymore. I want to see this total power. And this signal comes from the utility, from the system operator, because it wants to dispatch this power system to a given power, to a given prescribed power. So you can see these 2 lines here coincide, actually the reference power and the actual power. So what is said here, feeder head, sorry for the terminology, feeder head means just the actual power, aggregate power of this distribution network. So you can see that the power is dispatched to a given value, here it's dispatched to a lower value, and here dispatched to a higher value. And in addition to that, simultaneously, we also were able to regulate the voltages within bounds. So during this period, you don't have voltage violations anymore, and during this period, you don't have voltage violations. So that's, yeah, I think I will skip this. This is a bit of a sensitivity to noise. As you can imagine, these methods, based on measurements, are very sensitive to noise. Below some threshold, you can still do things. If the noise overcomes your exploration signal, right? Because things in this model 3 approach you need to explore, but if you have too much noise and the exploration signal is too small, then eventually you will not be able to explore. But I will skip that. I just want to give, okay, so that just summarizes this, right? So what I presented here was real-time primal dual methods to track desired trajectory of general network systems. Again, the application that we had is power systems, but you can think of similar approaches for other systems, which are connections of different systems in the network. We proposed this zero-order deterministic feedback-based approximations, showed some stability and tracking results, and applied to this optimal power flow problem. So I would like to finish maybe in a couple of minutes, really, just to give you a flavor. What else did we do? Of course, this is all theoretical, very nice in simulation, but I wanted to tell you that we actually went and implemented this in the field. And this I will do really, really fast, just to give you the flavor. So we have at NREL, we actually have different ways to go with different technologies and implement in real life. The first simple step from the simulation world is what is called power hardware in the loop, is where you take your algorithms and you implement them with real devices in the lab, but with some co-simulation of the other system, right? You can simulate the power system, you can simulate millions of other devices, but you also will have some of the devices, real devices, working in your lab in that co-simulation and emulation environment. So this is a very unique experiment. We had more than 100 physical devices with a realistic feeder from California, where we were basically coordinating all of these devices for similar things that I showed in the simulation, such as virtual power plant and voltage regulation. And furthermore, we went also to Basalt in Colorado. This is a project with Habitat for Humanity, and Holy Cross Energy is the electric co-op in this area. And what we did, we really took some of these algorithms and we installed controllers in people's houses, and we demonstrated some of this basic functionality in the real system in Colorado. Particularly here, I guess you're not familiar with this neighborhood, but this is a development that is going on right now. There will be 27 homes for teachers, low-income families in general in this area. Basalt, or this area is very expensive in general. This is where Aspen ski resort is, actually. So Habitat for Humanity built there these houses for low-income people. And the original plan was really to build zero net energy buildings with all electric construction. So we tapped into it. The first step was just to select 4 houses there and do a very small experiment with 4 houses, but we are also extending it in the future projects for a larger system. So I just want to thank the collaborators here and make sure that everyone is acknowledged. And I promised to finish earlier, but I see I didn't finish earlier. So I guess we have maybe 5 minutes for, Alicia, maybe you can take over from here and see what time is left.
Thank you. I don't know how we do virtual claps, but thank you very much. I'm afraid we have actually run out of time as we're sort of keeping to quite strict times. I have a bunch of questions, and I'm hoping that maybe you could actually hang out in one of our lounges and things. We have available online lounges, and maybe there might be some opportunities for us to ask questions, catch you some other time. But I think I'm going to have to not take questions at this point, but I'd like all of us to join in thanking Andrey for this wonderful and very, very interesting talk. Thank you very much.
Thank you, everyone.